number 2. Suppose you're not going to use them all. Suppose you've got a large group to pick from, but you're only going to use a smaller group each time, and you want to know how many ways can you arrange them in a line. So in this case, if I want to know how many ways are there to arrange 7 people out of this room in the front row, okay, there's more than 7 of you here. So how do I figure out how many ways there would be picking from, if everybody was here, we'd have 13. From picking from 13, how many ways are there to arrange 7 at a time? You can do it the way I showed you before. You can do it with the little blanks. If we're going to arrange 7 people, how many people would there be for the first spot to choose from? There are 13. Then okay. But can I do 13 factorial? No, because it didn't go all the way down to 1. Since I only wanted to use 7 people, it stopped right here. I'm not going to do 6 times 5 times 4 times 3 times 2 times 1. So, yes, this is, once again, this isn't a bad one. You could multiply that, like you could type that in your calculator and get an answer. But it's still kind of annoying to have to type all that in. So, once again, we need notation to do it. And so mathematicians created this notation. The P, capital P, stands for permutation. You're doing a permutation. Okay. The N and the R are going to be numbers you're going to put in. Okay. N is the total number of objects you have to start with. R is the number of them that you're going to use at one time. So for this particular problem we were just doing here, how many total people do I have? There are 13 of you, so I would go 13P, I'm doing permutations, I want patterns, and then how many was I going to use at a time? I was going to do 13P7. Okay, well the question is, how do you, A, calculate that, and B, how do you get your calculator to calculate that? Okay, I want you to know how to do this, particularly by being scholars, people. They like to ask this thing. I like to ask this thing. I write our math questions, so what your calculator actually does is it kicks it back to factorials. To calculate a permutation of n things that take an r at a time, it's going to do the total factorial, and then it's going to divide, and this is the part that the first is going to seem weird, it's going to divide by what you get when you subtract those two numbers. Now that seems strange. Why would it subtract them? And let me show you here with the 13P7. Following that rule, it's going to do 13 factorial, and it's going to divide by what? 6. 13 minus 7. Okay. If you actually wrote that out, and you don't necessarily need to write that out, if you actually wrote that out, I'd have 13, 12, 11. This is really fun. Over. What's going to cancel? If you actually write out all those factorials, what cancels? Doesn't 6 on down cancel? What are you left with? These first 7 numbers that we wanted up here in our blanks. So by telling it to divide the 2 factorials, you get the same result as saying, hey, take the first 7 numbers. Okay. For you all, you don't even have to type that far. You don't even have to do 13 factorial over 6 factorial. It's actually built in your calculator. You'll find it, of course, under menu, probability, since that's what we're doing. And you will see a choice for permutation. So, menu, 5 is probability, 2 is permutation. It will pop on the NPR. Okay, this actually annoys me. This is better on the old calculators. On the old calculators, I could put the number in where the N is and the R is. I could put it on either side of the P, which to me made it more meaningful to my students. Now, they make you type it in parentheses. So you would have to type, I had 13 people. You would have to get the comma, which is your bottom left corner is your comma, and then tell it, I want 7 at a time. And so, 8,648,640 different patterns we could make of people in the front row. The numbers are almost astronomical. It's like, whoa, geez. So let's write that answer down. There you go. So for you all, that's the easier way. But realize you have to put in a number, comma, a number in that parentheses or it does not work right. That's really important. But anytime they say pick 6 out of 20, you're going to range 5 out of 12 different group people to choose from. The NPR is the quicker way. So as far as what I want for a method, I want NPR. That's the method. Okay. Now, for the ones we always remember. Okay, guys, how many ways can you arrange the letters in the word Mississippi? I'll tell you there are 11 letters in the word Mississippi. I want to arrange all the letters. I want to know how many patterns can I make of the word Mississippi? Those letters. According to what we've done so far, I'm using all the letters, aren't I? If I'm just using all of them, I should just do 11 factorial and call it a day. But, nit kid on it. If I take these two S's and I switch their places, have I made a new pattern? If I take two I's and I switch their position so that it still doesn't make a different pattern. Because some of the letters are repeated, it's going to make you not have as many patterns. You're not making a different pattern. So how do we do it then if there's repeated letters? Well, in this case, you would go, I got 11 factorial. Then you have to divide out what you have that look alike. Okay, so how many S's do we have? There's 4 S's, so you're going to divide by 4 factorial for the S's. Okay, what else is alike? I's, how many I's? 4, so you're going to divide by 4 factorial again for the I's. Anything else that's repeated? P's, so 2 factorial for the P's. Okay, now somebody last block asked me a really good question. They said, well, can't I just add that up and divide by 10 factorial? Would that be the same? 10 factorial would be 10 times 9 times 8 times 7 times 6 times 5. This would be 4321 times 4321 times 21. Would not be near as big a number. So you know you cannot combine those. You have to do each one separately, which is kind of a pain to type in, but it's doable. Comes out 34,000 something or other. 34,650 different arrangements of the letters in the word Mississippi. Who wants to volunteer to write them out for us before next class? Pretty fun. Okay, as far as the formula goes, since this one can vary, I'm going to tell you it's the total factorial divided by each of the alikes you have. And there could be 2 numbers on the bottom. There could be 5 numbers on the bottom. It just depends on how many different things are repeated. But these problems, if I give you a set of letters, we always get it. But if I don't give it to you in that form, sometimes we don't realize we have alike objects. If you see a problem that says things look alike, or you'll see the word indistinguishable. Okay, so you cannot distinguish between them. You can't tell them apart. They look alike. Or you see it say that things are identical. That should scream at you, I'm a Mississippi problem. So if you see any of those words in a problem, that's a dead giveaway. Do the alike. All right, so here's an example that's maybe not so obvious. We got 4 footballs, 5 basketballs, 3 volleyballs. We're going to arrange them in a line on the gym floor. But, this is the important part, Balls of the same type are indistinguishable. What's that mean? I should have an S on it. If they're indistinguishable. The 4 footballs all look exactly alike. The 5 basketballs all look exactly alike. So you can't tell them apart. They're brand new balls. They have no markings on them. They all look the same. So how do I figure out how many ways I can arrange them or put them in patterns? Okay, there's 12 total balls. So yes, I would do 12 factorial. And then the 4 footballs look alike, the 5 basketballs look alike, and the 3 volleyballs look alike. So you would divide by each of those factorials. And you would get 27,720 different patterns you could make. Wouldn't that be fun to run the gym until you get all the patterns made? Okay. Last but not least, this is method number 4, by the way. I guess I don't have that written on there. I call this specific locations. If they tell you certain things have to be in a certain position, or if they tell you you can use something more than once, repeated, okay, then in this case you can't use factorials, because if they're saying certain things have to be in a certain position, factorials aren't going to work. So I'm going to tell you the only way to do these kind, if they put specific requirements on it, you have to draw out the little blanks and fill the numbers in each blank. There's just no other way. You just got to do it one spot at a time and go, how many choices do I have for each spot? Okay. Actually, we're filling the second row again. 2, 4, 5, 6, 7, 8. I'm telling you I want juniors in the 2 middle seats, and I want sophomores out on the ends, and the other people, I don't care. So I'm going to make a line of people. Sophomores have to be in the ends. I have to have 2 juniors sitting in the dead center middle. How do I figure out how many ways I can arrange you all? Choosing from you all again. Okay, I will do just how many are right here right now. So how many sophomores are in this room right now? 5, okay? So when I go to sit the sophomore down, there are 5 choices. But now I need to do the other sophomore. How many choices are there for that sophomore? There are 4, okay? So do the specific positions first. Okay, now I need to do the juniors. How many juniors are there at present? 7 in there? Okay, so there would be 7 juniors to sit in the first spot. Then how many? 6. Okay, now here's where we usually stall. The other seats can be anybody who's left. Doesn't matter who. They can be a freshman, sophomore, junior, senior. Doesn't matter who it is. So how many people are still left? Because if there are 12 of you right now, and we've seated 4 people, there are 8 of you left yet that haven't sat down. You're still standing up. So therefore, when I go to fill that one in, there would be 8 people who could sit here, then 7, then 6, then 5. So you don't have to do, it's okay if you have the same number in the twice. This is not going to be factorial. It's not going to work the same because you're putting certain people in certain positions. It's not necessarily going to follow a factorial pattern. You would simply have to multiply all those different numbers together. And then one of you has to do that because that's bigger than my brain is going to do. 40 times 20 is 800. So then it gets hard. So, what's it going to be in the thousands, the 100,000s, the millions, the billions? What do you think? What? 20. So 2,257,920 different ways we could put people in one row. Hope nobody's going to try that. All right. Now, my last question while we're doing linear permutations. How many Kansas license plates are possible? Not with custom-made ones, just with our normal pattern of license plates. How many license plates are possible with our system? Well, what is our pattern on our license plates? We're actually letter, 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 followed by number, number, number. Okay. So I know I have to have letters in one spot, numbers in another. That's why I had to do a drawing blank. I can't just do a straight factorial. How many letters are there that I could have? There are 26 letters in the alphabet. Okay, so how many are there for the next blank? Why did she say 26 again? Yeah, can't you repeat a letter? So, yeah, it stays 26 this time. Okay. So there are 26 letters each time. Okay. Now, this will always get this. How many single-digit numbers are possible? You always tell me 9, but 1 through 9 is 9. What about 0? You don't see 710? I was thinking I had one with a 0 one. I think there's zeros. Well, we're going to assume there's zeros. So that means there's 10 single-digit numbers then. 1 through 9 plus 0. How many for the second slot? 10, because you can repeat numbers too. And 10. So if you multiply that together, it comes out, I changed this problem, it comes out 17 million something. What? Say 17,500,000 and some thousand. And it's going to have zeros on the end. 576, okay. So 17,576,000 different license plates are available in Kansas. That sounds like plenty. Shoot, our population's not even 3 million. But how many vehicles do people own? So yeah, so you can't just have one license plate per person. Yeah, you may have multiple vehicles. So, and that's not all the custom license plates and the commercial license plates and all that other stuff. But now, have you seen license plates from like California or New York? What's the difference about their license plates? Yeah, they may have 4 or 5 letters on theirs because they need way more license plates than we do here in Kansas. So you'll see them when they add more. When you add another number to multiply by, think how much bigger that 17 million gets. If I put another 26 out there, if I can take 26 times that 17 million by adding a 4th letter, that gives me a whole lot more license plate choices. Now, who wants to be the dude who gets to print all those license plates?
So what's the formula?
Yeah, that's the method. The method is draw blanks and fill in the numbers. That is the method.